where is the question? There are not much field theory on magnetic field in high school. What I mean is that we simply introduce a B. We introduce the B to describe the magnetic field, right? You remember the B, the vector. And by definition, this is not called field strings. If you want to know the full name, it's called this is a represent magnetic field flux strings. That's full name. Do you mean that? So basically, this of course we can simply say the magnetic field for short, right? That is a full name. So unlike electric field, we also use E for electric field, and then we use G for gravitational field, right? And both of them are called field strings. Can you see? It's called a field string without this flux. Can you see? Because if you introduce field strings, then we can in both cases we can introduce another vectors. In this case, can we say dv dr? Can you see? Similarly, I will put this E for electric field. Similarly, we can also write G as dv d. Sorry, not dt dr. Have you seen this formula before? This is G, gravitational field strength. So what is V? VE is a potential. You see, is potential. Potential. And also a VG is also potential. So one is electric, another gravitational. Have you studied these two formulas before in physics?
No.
No. So I just give you some background. Doesn't matter. When we study magnetic field, right? We cannot have this simple relation like a potential, right? So of course, if you continue study physics in the university level, you will see that the B can be associated with a vector, another vector potential, but it's beyond high school topics. So what is magnetic field? Magnetic field is to describe, when we have the flux, can you see? If you choose the area, so this is A, so this is area. If you can visualize that the magnetic field go from one, can you see? Not necessarily uniform, but it goes through this area, can you see? If magnetic field goes through that area, then you can argue that we can use the B to describe this flux intensity, the strength. Okay, just like a pipe of water, can you see? The more the motor goes through the pipe, and the higher the water flow is. So in this regard, magnetic field looks like something flow, okay? But it's not nothing flow. It's just you can imagine that something is flow in the space. So do you remember the related idea? So another idea is magnetic field flux. So that is how do we define magnetic field class? We just go backward. You see, what is magnetic flux? Do you remember? We use phi to represent in Greek letter.
A B cos theta.
Yes, that's right. So phi, by definition, phi is a flux, and in simplest case, it's just B multiplied A, isn't it? Okay. So from this simple relation, we can argue that B is equal to flux divided by area. Can you see? per unit area. So does that make sense now? That is a flux strength. Can you see?
Yeah.
That is a full name of the B, or simply called the magnetic field. Okay.
Mm-hmm.
In general, so this is special case. So in general, we know that the flux can be simply written, should be written as a dot product. Okay. B dot product A. If you use yesterday, last time we're talking about the unit vector. Do you remember yesterday, Wednesday? So this is a unit vector represent, which is a perpendicular to the A. You see? So this is a unit vector. This is a unit vector. This is a directional vector, and this blue colored one is B. You see? And that is if you use this unit of n to represent the direction perpendicular to the A, that would be the more general form. You see, in this case, you can write that as a BA multiply cosine theta. If the theta, if there's an angle, can you see? In this case, the angle is almost 0. So there is angle, can you see? There is an angle here. After you have started calculus, then you can actually work out the more complicated. I just use, because you have started the calculus, right? If you go to general case, if you consider not a very small area, even you can consider, let's draw something. Let's go to more general. Say, can we consider a sphere? Can you see? Can you consider this is a part. This is a semi-sphere. Can you imagine that? This is a semi-sphere. Can you see that? So if you want to know, for example, in this case, if the magnetic field goes that way, it goes that way, and the magnetic field goes that way, and that enter to that way. Can you see enter that to that way? So this is a more general case. Now, how can we work out this flux of this semi-sphere? Then we have to invoke the calculus. Just denote that this is n direction of this very tiny small area. Can you see? This is a very tiny small area. Because it's so small, we can use this formula to represent this tiny area. Can you see that? However, in general case, what you have to do, we have to use integration. You see, we use a B dot dA. dA means very small area. Can you see? This is dA. See that? That just remind you, because you have started calculus, right? So that is how we can use the calculus to work out the flux in general case. But in high school, we only focus on this formula. That's sufficient, all right?
Yeah.
And so we just remind you, so the flux can have different form. The simplest form is that in this case, we know that it's a special case if theta equal to 0, right? Then that the flux is just simply the product of 2. I'll give you another example. For example, when we study the electrical generator, so we start electricity generator, so electricity generator. So how do we generate electricity? Well, we can use a 2 magnet, permanent magnet. One is a north, right? That is another place where you can use this flux. On the other side, we use S. So this is a 2 pole of the magnet, permanent magnet. So in this setup, the magnetic field, can you imagine, is from the north to south. Can you see? Between the gap, between the 2 gaps, can you see? But of course, outside gap is not simple, all right? But we only focus on the magnetic field between these two gaps. So this is B vector. Now, how do we generate electricity? We can just using a coil, which is imagine there is a rotation. There's a rotating axis. So we can use a coil. For example, we use a rectangle coil, right? We use a rectangle coil here. Can you see that? This is just a rectangle coil here. And you can make this colored one is made by metal conductor. You see? So in this way, when it's rotate, you can imagine that when it's rotate, when this coil is rotate, and the current can be generated according to the Faraday's law. The Faraday's law say so this is generator. So this is just equivalent to a AC power supply. Can you see? It just is this notation. This is just AC power supply for electrical generator. Now, according to the potential, the voltage is called across them is called electromotive force, right? The epsilon is equal to the number of turns. I just go through this basic formula, and the d phi dt. Do you remember this formula? And that is very important formula for studying the time-dependent electromagnetism. Now, in this case, how do we work out in this particular case, how do we work out the flux? Can you tell me? If this longer side is A, this side is a B. Can you see? How can we work out the formula for the phi, the flux, this time? So what is A in this case? A, not the direction, but the size of A is just A multiplied B. Do you agree? Now, the question is, what is the size? What is the angle? So we have to show the angle here. Can you see? We still use the directional vector here. Can you see? Which is perpendicular to this rectangle. So in this case, the angle between, can you see this angle? That is angle between this N and the magnetic field. If we call the theta, right? So that is, if that is a theta, the phi will equal to, you can imagine in this case, I probably draw this diagram over here. So magnetic field is, in this case, magnetic field is parallel, can you see? And in this particular position, the theta is different. Can you see? That is theta. It's this is not theta. This is N, the directional vector. This is the theta. You see that? It is a B, the magnetic field. So, according to this formula, can you see? For this formula, we can write that this would be the dot product, which is equal to B multiply A. A is just A. We just write A here, and multiply cosine theta. Can you see that? So what is theta? So theta is if you use theta, this is theta. Can you see? So as theta can be written as a function of the time. Can you see? The theta is always turning. Can you see? So the simplest formula for theta is theta equal to omega t. Can you see? Do you remember when we studied simple harmonic motion, we use omega, right? Omega there is called angular frequency. In this case, omega here is angular velocity. Angular velocity. In other words, that represents how fast the theta change, all right? That will give you omega is equal to d theta dt, you see? So that's why we call it angular velocity. Okay. So if you substitute that one, then we should be able to get this output. So that is induced current, or basically N is the number of the turn, you see? When we build this coil, if it's more than one turn, we have multiplied number of turn. Is that what is this topic? What I'm talking is you just asked about magnetic field.
Sort of.
Any other issues related to the B?
This is
well,
one.
this story can go on for a long time if you don't let me know which is specific question you are looking for.
I think it's about solenoids.
Aha, yes, solenoid is not an issue. So if you talk about a solenoid, so which is a very example solenoid, yeah. Solenoid is coil, right? It's a coil, which is built to generate use electricity to generate a magnetic field. Okay. The basic idea is that you can have the core. This could be just air core. You see, it's empty. You can use a paper or use a plastic to make the core with a cylinder, right? It's empty inside. Okay. And what you do next is you just use a coil. You just put the conductor. You see, put a conductor here. You see. Of course, in the real case, you can put more condense, all right? Here, I just draw this one, just allow you to, you can actually see how the direction of the coil goes. You see, it must be uniform, the better. So you can count, can you see? So you actually can count how many turns, right? Yeah, sometimes this is a solenoid. So why do we need to use a solenoid? Because sometimes we need to generate a magnetic field. For example, in this case, if we connect them with a battery, for example, right, or two, and then what would happen once we switch on? Maybe you should put some resistors, otherwise the current will be huge, right? We put a resistor here just to control the current. So which direction? Can you indicate what would be the direction the current will go? This is positive. Once we switch on,
it'll move from positive to negative.
Yes. So if I draw the direction, that would be the direction. Do you agree with me? That's the direction. Can you see?
Yeah.
That is current to go and eventually return to the negative pole, right?
Doesn't it go from negative to positive?
For that convention, yes. The convention is that the current go from the positive to negative, all right? Another issue is that because the conductor, in terms of conductor is basically, can we just imagine this conductor, right? So conductor is made by metals. Good conductor is like kind of copper. So basically, if you enlarge that, if you want to go to detail, you will see that the conductor wire, here I just presumably this kind of represent the copper. And inside there's only negative charge, which called the free electron that can move. You see, so you have negative electron. In the presence of charge, these electron can move in the direction according to the applied voltage. If, for example, if you apply this, if we just apply the positive here, negative here, so which direction? So this is positive. So which direction does electron go? Can you tell me?
The other way to.
Yeah. So electron will move here. Can you see?
Mm-hmm.
As far as electron will go that way. Can you see? That is opposite. Can you see? So
Yeah.
in other words, electron in chemistry we use this notation, right? The negative E. But that is what happened in the conductor. However, the idea of the concept of electrical current was introduced before the discovery of electron. So actually, it's American Benjamin Franklin. Have you heard of Benjamin Franklin?
Yeah.
If you have say the donor sign, the donor, US dollar. Okay, his portrait there. So he actually also he spent a lot of time to study physics, electricity in particular. Actually, he was the first person to demonstrate that lightning during thunderstorm is electricity spark. Anyway, now because of him, he said, well, let's just assume that current go from positive to negative. So we use this convention all the time, all right? So the electric current we say is go from positive to negative. Until after we found that the electron is moving to opposite direction because there's no positive charge. The positive charge cannot move in the metal, all right? However, in chemistry, that will be different. In chemistry, have you studied the electrochemistry? Not yet.
I don't think so.
Ooh, I think year 12, you were going to you were saying so. Basically, in chemistry, the ion can have two signs. Do you agree?
Mm-hmm.
So
oh yes, I know this.
Yes, you say that's due to Faraday. If you put a positive charge, this is a positive charge here, so this become a positive road. Can you see? So this will be negative. So because in the ion we got different charge. Can you see chloride negative, right? Sodium is positive. Other way around? Yeah, that's right.
I think that's right. Yeah.
That's right. So which direction does this charge go?
The electrons move from positive to.
Well, forget about electron. Just forget about these two ions, not larger than.
The Cl will go to the positive.
Yes, that's right. Can you see? And the positive, these were that. Then here you can count the positive charge, right? So that is how you to describe it. Can you see?
Yeah.
Don't worry, because when we talk about solenoid, we just assume we with the current direction. All right. We don't pay attention to the actual direction of what is the electron move. Okay, but we can explain that, right? As I have just explained to you, right? So it's convention. It's convention in electricity that the current can go from positive of battery to the negative. That's it. All right. Anyway, because that direction is matter, this direction matters because that will determine us how to identify the magnetic field generated. Can you see? As a result, the magnetic field were generated. Can you see?
Yeah.
Now the question is, how do we determine the magnetic field generated inside this solenoid coil? Do you know how to do that?
Is there a formula for it?
No, we use the right-hand rule. You use this is a coil. Can you see? So this is a coil, and you just use 4 fingers. Can you see? Trying to hold this coil, but when you do so, the direction of 4 fingers must be in the direction of the current. Can you see?
Yeah.
And the direction of the thumb will automatically give you direction of the magnetic field inside this solenoid. in this case, the magnetic field generated by this electricity will go that direction. Can you see?
Mm-hmm.
Inside coil. Okay. And
Yeah.
another thing is that inside the coil, the magnetic field is uniform. So that is why, imagine, so if you just, for example, when we do some experiment, we always say, well, let's say the field is into the page, all right?
Mm-hmm.
So how can we achieve this uniform magnetic field? That is use a solenoid. One of the ideas is a solenoid. Because you cut off any, if you cut off any section inside here, can you see any section here, right?
Mm-hmm.
And the magnetic field is always uniform. Can you see?
Yeah.
That is a device, one of devices to generate a uniform magnetic field. But more importantly, if you extend, you may ask, so what would be the electric? Can I ask you what is the direct distribution of magnetic field outside solenoid? Can you complete that diagram? If inside is go that way by the right-hand rule, what would be the distribution of magnetic field outside a solenoid coil?
Is direction. Well, is it the other way around?
No, yeah, you can draw that because this solenoid is actually equivalent to the magnetic field. I mean, the outside.
This way, outside of the solenoid?
You go on. Yeah, outside solenoid. Yeah. Oh, no, not that way. No, you have to make it continuous. You can make it continuous. Can we consider another example which we discussed before we started the solenoid, which is a permanent magnet? Can you see?
Mm-hmm.
So this is a permanent magnet. This is the north. This is the south. Do you remember? Do you remember the distribution of magnetic field of the permanent magnet? From the north, can you see? From the north and back to south, can you see?
Is it?
Yes, so, and around that would be the direction of the magnetic field. Have you seen this diagram before?
Yes.
Yes, so that it's time to use this idea now, because experimentally we can demonstrate this distribution by using a proper experiment. Did the teacher do an experiment to show this distribution, which is invisible, by the way? These magnetic field line is called force line. So this is called the force line. It's called the force line. Because I tell you why we call it force line. Magnetic is force line here. The reason we call it force line, if you put the compass, if you put a magnetic compass, all right, and the compass will automatically make in alignment. So the compass has north, can you see? The compass has north, and also they have south. They automatically make alignment, so that this needle is parallel to this in tangent direction. For example, if you put the compass over here, all right, and that needle will point to that direction. Can you see that? Which is always along the tangential direction. Okay, that's tiny compass. So you can see the force, the magnetic force is always force the needle to move so that they will become parallel at each point. Now, the question is, what is the difference? What is the similarity in these two devices? This is magnet. So this side is a magnet, permanent magnet. And on the other side is the solenoid with the electrical current.
So it's electromagnet?
Electromagnet. So therefore, we can argue that if we continue that diagram, then you will see the similar distribution. Can you see? Yeah. From north to the south. Can you see? See? So that's in. That's from. That's not out. So not opposite. Can you see? That's come out. This sorry, come in. Come in. From. Oh, hang on. I draw. My direction is wrong. Sorry. It should be like this. Can you see? That would be because that direction. Can you see? From north to south. So from north to south. Can you see?
Isn't the North Pole the positively charged pole?
No, in this case, the North Pole will be here. If you do want to for which is north, this will be the north. Can you see? This will be the south, because that ended.
Oh, right.
Ended with the electrical, magnetic force line ended at South Pole. All right. So you can see that I can draw more another pair. This diagram is useful when we study the phenomena of the induction. You see. So that's instance basically that is how the field distributed. You see. Now you can compare what is the similarity between the solenoid, the field, magnetic field generated by solenoid, and the magnetic field generated by a permanent magnet. What is the difference at the similarity? That is you see in history, and the ancient people even know that how permanent magnetic field work. They attract. Can you see? The reason they make this assignment is because they can make the compass rotate. Because if you put the two magnet, and then you will see the attraction. Can you see? In other words, can we draw that? If you put a two magnet, and if you put opposite, if you put opposite pole together, have you attraction? Yeah, can you see? That's north, south, north, south. In a similar way, but not exactly the same way. Okay, they were narrow this gap. Can you see? So the attraction between these two. Then when you put the two together, they will simply form a new magnet. Can you see? It's very interesting. After this, if they join together, and you will get the new magnet. Can you see? The length is doubled. The length is doubled, but the pole is just the two. Can you see? It's very interesting. So you get the new south, north, and the south. Can you see? So that is a property of a permanent magnet, and this property is similar to this one. You know the positive charge and negative charge. And in this, according to Coulomb's law, the attraction. Can you see? They have attraction. Yeah. But the force, the formula for the force are different, and also the nature of the force is different, because that is why in history, for many centuries, we studied the magnetism and electricity separately. So that is a magnetism. That is the electricity phenomena. Electricity. You understand? Electricity was magnet was studied separately. However, when you talk about solenoid, that was the first moment people realized electricity and magnetism are not separate. And when Faraday first discovered this phenomena, he just noticed that they got the metal wire which has current goes through. So the current is goes through that way. You see, that is a current. And when he did the experiment, just by use battery, use electricity, to his surprise, when this current move is on, and the compass here rotate accordingly, you see, the compass is simply as this. The compass is, can we just do a simple one? So the compass is just like this have north, have south, can you see? So this is a simple compass here, can you see? So one of the direction is north and south, can you see?
Yeah.
So without the current, the compass is just not put into south, and this south pole and north pole. Oh, I got this one. I probably use a camera for it. Can you see? So this is compass. Can you see?
Yeah.
Without turn on the electricity, this compass, like any compass, they just point north and south. All right. However, when they switch on the current, if this compass is closer to the wire, and they will change the direction. They will change the direction slightly so that they can satisfy. They will no longer point south and north of the Earth. Did teacher show this before? Did the teacher demonstrate this phenomena before? One moment. Share screen. Did your teacher do this experiment before? No?
No.
Oh, that's very interesting. In Stay High, they don't. So basically, what's happened now, gradually, Faraday understand. Once we got the current going, and they will generate magnetic field. You see, which was totally new idea. In a circle, can you see? In this direction. Of course, the strength is getting weaker as the distance increase. Can you see that? So that is a magnetic field generated by the magnetic field. By this magnetic field is generated by this current. Can you see? When you switch off, the magnetic field disappears. So you can imagine that perhaps that at the beginning, this compass is moving to the south and north in different direction. Can you see? And so when they turn the current on, they will rotate a certain angle. Can you see that? In the same manner as this one, can you see? If you put the compass here, the compass will always orientate this way, so that the north is where the direction will in the same direction as this they call the force line. Can you see? So that is the first time. That is the first experiment. That was what Faraday discovered by accident. He just simply used. He just doing the electricity experiment, but he noticed that compass is moving. So eventually, he discovered that the magnetic field can be generated by electrical current. Oh, by the way, do you know how to determine this current direction? If the current go up, how do we Did your textbook, did your teacher show you how to determine this direction of current?
Direction of current should be the thumb, right?
Yeah, if you hold, then use the right hand. Always use the right hand. Can you see? If you use the forefinger, hold that a wire, the thumb, if the thumb is the direction of current, then the magnetic field will follow your four fingers doing the circle, forming different circles.
Yeah.
Aha, so this is another device. By the way, do you know the formula generated by this device? So if this distance is r, can you see? So this is P, the point P. If you want to find the magnetic field strength at this point P, the P is simply equal to, it's called nu null. That is the property of vacuum, magnetic property of vacuum. It's called nu null divided by 2 pi r multiply the current. So simple. Do you know this formula?
Yeah.
Ah, yes, good. So in other words, so if you want to draw, the this is r, the distance from wire, you see, and the strength of magnetic field will simply decrease like reciprocal function. Can you see? All right. If you're getting closer, the magnetic field strength increase enormously. So that, well, gradually from this phenomena, eventually people invented this solenoid. Can you see that? Solenoid is a better way. Another device to generate a uniform magnetic field inside the cylinder. You see? So do you know the formula for the cylinder field, magnetic field, chemical B? That is the formula we need to know. Of course, it must be proportional to the current. Do you agree?
Yeah.
And also, this constant is there. But in addition, you also have this number. So how many turns? For example, can you put n here, right? And divide by the length of this cylinder. You see, the cylinder is full of the coil. So that will be determined by the length of this coil. Do you know this formula? I double check.
Yes.
Did the teacher use this formula?
The formula we have is.
You can write down any other formula. You know.
But
yeah, small n. So what is small n?
Equals n over L. So
the same formula, right? It is same formula. That's good. Yeah. So you can see, since the discovery of these are the electrical magnet, right? The magnet field generated by electricity rather than permanent magnet. You see? Oh, by the way, the difference between these two devices is that outside this device, the distribution of magnetic field is the same, but inside the magnet we don't know. All right. Inside, in the solenoid, we know the magnetic field will go continuously, right? But inside this one, we don't know. Okay. Because we cannot enter, because these are solid. We will not enter that into the magnet. So that is some of the background of the solenoid. Another thing, probably I'll extend our discussion. If we reduce the solenoid to the single, can we just reduce the solenoid into the single coil? What would happen? So this is a paper coil. Can you see the paper coil? If I just reduce into the single coil, can you see? Okay, so that is can you see? Just one turn. Can you imagine? There's just one turn. Can you describe the distribution of magnetic field in this case? Can you describe the magnetic field distribution? In other words, can we just draw this one? Probably, if you have this is just a 3D diagram. Can you see? If I just let me finish this drawing. If I just, can you see? I cut this. This is a single turn. This time, I just connect that. Okay, I connect this single turn. It's just like basketball net, right? And we put a battery here. So this is a battery, positive, negative. And we just put resistors here. Can you see?
Yeah.
So the current will go that way. Can you see? The current will go that way and go that way. We just assume that this is up. Can you see? This is up. So this is direction. This perpendicular direction. Can you see? Okay. In this case, can you draw the distribution of magnetic field generated by this single turn coil? Is a single turn coil.
If current goes up.
Coil. So you can use you can continue use you can still use the right hand rule, because right hand will say the current, if the current goes that direction. Yes, that's right. Yes, that's right. Yes, right. I can edit more. Yes, that's right. So we can edit more, so that go that direction. That's right. They just improve they became complete. They became the complete circle. Can you see? Complete circle. Everywhere they became complete circle. Can you see?
Yeah.
Okay. So you can imagine that the magnetic field at the center, is like this. Can you see? Magnetic center at the center is like this. Can you see? So this is the north pole. Do you agree? So this side will be north, right?
Yeah.
Now, if you know this,
the current would have to point down, wouldn't it?
Sorry. So from so this will be into the page, into it. Yes.
But if the current points up, then we can't get the direction of it.
Say it again. If we change the direction or we keep the direction of current, what did you say?
Using the right-hand rule.
Yeah.
The current would have to point down, wouldn't it, if we did the thing?
If I use, let's just say, if we use the right hand and yes, we have worked out this correctly. Can we redraw this diagram? Be careful. Yes, a good question. Can we redraw this? Can you draw this one? Yeah, can we draw this? Yeah, according to the so this is behind because this is just. So if according to the right hand rule, the field inside is downward. Yes, you are right. Yeah. So field inside is downward. Can you see? It is into like this. Can you see?
Yeah.
Into the page. Okay. So that is so if you extend that, yes, be careful. The direction, direction. This is correct direction. Can you see? That would be correct. Outside is up, but inside is down. You are right. Can you see? Yeah. Can we draw another circle? So this is another circle. Can you see? There's another circle in which inside is into the page. Can you see? Into the page. Good point. So that will be like this. Outside is like this. Can you see? I can draw more. Can I draw another one? Can I just circle it? Okay. So that would be like this. You're right. So that is this is up and down. Can you see? So in that case, this would be the south. Can you see? Upside will be south in this case. So if that is a magnetic field, so that is into the page, can you see? Into the page. So therefore, the magnet as a whole must be like this, upward, can you see? So this one is enter, can you see? Into the page and out of page, can you see?
Yeah.
So that is good, that is distribution. But for solenoid, inside is a uniform, right? Now, if you know this idea, then you will know that the origin, if you understand this idea, then you should be able to understand what is made of magnet. Return to the basic question in electromagnetism. Okay. I said if I put the two magnets together, they will become one, all right? However, if you cut the magnet into two, what would happen? Cut it to half, what would happen? I just you can I just think it backward. Can you see? If this is so this is north, can you see? You cut into two. You got two small magnet, but still with two poles. Can you see? Now this is the same idea. If I just go further, if I cut it off by half again, what would happen?
It would become smaller.
Shorter, getting very shorter, right? Getting shorter. But it's still got two poles, can you see? It's still the single magnet. Now, if you continue to do that for many times, what would happen? Do you remember? Oh, another student asked me a question. Do you can you imagine that if we continue to this cut, can you see this is the length is this length is 1, can you see? And this length will be the half, can you see? This length will be quarter, do you agree?
Yeah.
In other words, if you put the geometrical sequences, that would be the 1. That would be I put the that would be 0. Can you see? Cut it once, that become 1. Can you see? Can you see the geometrical sequences? This is 1.
Yeah.
And that would be half square. Okay. If cut is n time, so n time, if you half n time, halved n time, can you imagine what would happen? What is the length? What is the final length?
1 over n squared.
Yes, halved n time. That is a little bit of the math now. So eventually we got to this 1 over, can you see?
2n.
1 over n, very small number, right? Now bear in mind, so what is the size of atom? What is the size of atom? Do you remember? What is the size, diameter? Hydrogen atom. Have you studied this idea?
It
must be very small.
I'm not sure what
diameter is very close to 10 to power negative 10 meters, right? So that is the size of atom. So if this go on, if n is not enough, we will eventually get atom. Do you agree? How many times can we see the size of atom? So we just need this. This is a dn. Can you see? This is dn. We just need the dn equal to this number. Can you see? Okay. That in that way we should be able to solve this n. How can we solve this n? Use this equation. What is n? Can we just rewrite that as a 2 power n equal to 10 to power 10? Okay. That's right.
Isn't it 1 over 10 to the power 10?
Let's double check, because we multiply, we divide, you see, we exchange, we divide. So that's 1 over or 10. Can you see? Is that right?
I think so.
Yep. You can use calculator to work out this number. You can use logarithmic. Can you see? Can we use a log 10? You see? We got n log 10 log 2, right? Equal to 10. Do you agree?
Mm-hmm.
Log 10 is equal to 1. So what is n?
And
So
oh wait, no, it's not.
what is n? That's a little bit of math now. It's 10 divided by log 10, right? Log 2, sorry.
Yeah.
So what is n? Can you, before you go to calculator, can you guess 100 times, 300,000, or 50 times? How many times? Or what is n roughly?
Like 50.
50? Oh, how very close. Yeah, how do you know?
I just guessed.
Oh, you guess, okay. Well, other people would say 1,000 times because an atom is so small, right?
Mm-hmm.
Anyway, can you find this n by calculator, by using a calculator?
33.22.
33, wow, 30, yes, 33 roughly, right?
Mm-hmm.
So you just half the 32 times, you will see the atom, all right?
Mm-hmm.
Now, the question is, the challenge question, do we still have permanent magnet when we say atom? Single atom, can we imagine the magnet made by single atom? Is that possible? No, you see, by n, if n is, if say n is equal to 33, right? We should be able to see the single atom now. Can you see?
No,
Why not?
it's too small.
No. We are talking about the size. Well, seriously, after half 30 times, 33 times, that's what the equation say. We should be able to see hydrogen atom. You don't believe that? Don't believe that? You still you work out as a number, but you don't believe it. Is that right?
Oh, well, the hydrogen atom would be like a magnet, but we wouldn't be able to see it, would we?
Well, that is the question. Yeah, that whether we can see this atom is not, but what the question is, we no longer have a permanent magnet. We have a single atom. The question is, how do we use this single atom to explain the magnetic field? Then we have considered use a Bohr model, not a Bohr model, use a Rutherford. Well, you can use Bohr model as well. Can we imagine the electron is doing a circular motion?
Yeah.
It is, right? So this is electron. So therefore, the current were generated if that electron moving to that direction, okay, and the current will be generated to opposite direction. Can you see? The current were generated in opposite direction. Can you see that?
Yeah.
Can you see similarity between this single core coin and our hydrogen atom? Can we find the direction of the magnetic field generated by the moving electron?
It would move up.
Yeah, move downward. Yeah, should be
No,
downward.
it would move down. It would move
downward. Okay.
Yeah.
So let's just finish that diagram. So that is a very important idea. So the origin of magnetic field can be explained by the motion of electron. That makes sense now. Everything, magnetic field is not generated by oh well, at a very large size. You can see you can use a permanent magnet to generate a magnetic field. Do you agree? But it took physicists 100 years to realize that the origin of magnetic field is due to the moving charge inside atom. Can you see that?
Yeah.
That is a story. Probably your textbook will not tell you this. Can you see? If this phenomena is similar to this idea, can you see? We use a battery here, and that is this is upward. So the current will form. Can you see? As a result, the magnetic field were generated downward. Can you see? Oops. So that is the explanation of the origin of magnetic field by use of solenoid. Can you see?
Yeah.
Makes sense now? So that is a big unification of electricity and magnetism.
Yeah.
Magnetism is no longer separate from the electricity. All right. Well, that is a non-story, isn't it? Well,
yeah.
Just after that, just think about this idea again. Can you convince after 30 times half any permanent magnet will reach to the single atom? All right. I will save that. Okay. All right. Take a break now.
Yeah. Okay.
See you next time. Goodbye.
Yeah. See you next week.